we've come to the last of our little series on how to find areas of shapes. I started, as you might recall, with a rectangle, and everything since then has been based on the idea that the area of a shape is its length times its breadth. And I'm going to write a little bit of a summary. For those who've looked at each of the videos, we started by saying that the area for a square, a rectangle and a parallelogram is length times breadth. The area of a triangle, a kite and a rhombus, for all three of these, was length times breadth over 2, because all three of these fitted inside a rectangle and used up half the space inside a rectangle. We worked out that the area of a trapezium with 2 lengths and a breadth was length 1 and length 2 divided by 2, in other words, average length times breadth. And we found that a circle with a radius r, of course, had an area of pi r squared, and we were able to derive that in a kind of way by cutting the circle up in a rather clever way and forming what was a pretty close to a rectangle in shape. So that was our first video or collection of videos. We then looked at the trapezoidal rule, the areas underneath, we looked at composite areas, which really is not relevant here. For areas underneath curves where we had a trapezium, we're using this formula. And we'd say the area is approximately, if this was y0 and y1, and this here was the breadth, or width or height, whatever you want to call it, it would be y0 and y1 divided by 2, in other words the average length or the average ordinate value times the breadth. That's not the standard way textbooks show it, but I was trying to get the concept across that it's length times breadth, or average length times breadth. So I'll write here trapezoidal. Rule. And then we looked at Simpson's rule. This time we've got a curve with 3 ordinate values. We'll call them y0, y1 and y2. And again we have the breadth. And we worked out the area was approximately, this time, y0 and 4 lots of the middle value and y2 divided by, and because we now have not 1, not 2, not 3, but 1, 2 and 4 more, that's 6 lengths averaged, we divide by 6 times the breadth. And that was Simpson's rule. If you didn't see that video, you can go back and look at it. Again, that's not the, well, that's pretty close to the standard notation actually, the Y notation. The last thing I want to mention is integration. Now, I'm certainly not going to deal with this in great or precise mathematical detail. I'm just simply trying to get a concept across. And when we're finding the area under a curve using an integral, what we're basically doing is dividing the area up into lots of very, very, very tiny strips. Now, if you're a mathematical purist, please forgive me this description, but basically this is the way I convey it to students. We're dividing it up into minuscule, very, very tiny thin strips, and the strip height here is y, or fx. If if this is the x value along the x-axis, so at that very position, that ordinate value is the y value or the function value, and the width of the strip is what we call dx, a very tiny portion of the x-axis. And the area of that rectangle is the y value times the dx width. So the y value times the dx width, or I'll put equals the function value times the dx width. Either of these are good expressions for that thin little strip. And if we add up all these strips, the theory is that we get a value for the area under this curve, and there are things called limits involved and so on, but the basic concept is we add up all of these little rectangles. Now, to add them up, we use an old-fashioned English S. In the old days, if we go back to Greek, for example, Greek had two letters for S. They had this one, lowercase sigma. Actually, the original Greeks just had capitals, but here we have a lowercase sigma, and that was used in the middle of words, and at the end of words we had a slightly more cursive looking S, from which we derive our S. Similarly, in the 1700s, the S they used in the middle of words was a very long, elongated one, and they used an S like this at the end. So you had things like this word, success, was written in this form. I might actually put an overlay so you can see this symbol from, I think it's the American Declaration of Independence that I was seeing on the internet. Again, dating from the 1700s, of course, and it uses this sort of writing. And people in that day used this letter S to say we are going to sum or add up all of these rectangles. We're going to add up the rectangles, and that's where we get the symbols from for finding integrals. I'm not going to explain how to do it in this video, or to do it in a very detailed mathematical way. I just want you to see length times breadth, average length times breadth, a length times a breadth, r times r, average length times breadth, average length times breadth, length times breadth, length times breadth. All of our attempts to find areas involve multiplying two values, two lengths together, a length times a breadth. And I hope that has sort of tied together our area finding skills for you. Please comment in the area below the video, leave a constructive criticism if you wish to. I certainly would appreciate accolades if you find this is useful. I'd love you to like this video and please subscribe so you find out about future videos that I'm producing. And if you want to see my website or Facebook page, please click on one of the links below and enjoy what you see there. Thank you very much for watching.